Hello and welcome to episode 9 of Calculus 1. I am Mohammad Momenzadeh, the presenter of this lecture. Today we will discuss about the remaining part of the chain rule and application of a chain rule to calculate some type of the derivative, and then we will reach to the implicit derivative as well. We will discuss about the implicit derivative. If we just take a look at the topics that we have it, so we already discussed about the product rule and quotient rule, but the implicit derivative and inverse function derivative will be discussed. At the end of the day, we will talk about some application for the exponential and logarithmic function as well. So let us go through the topics and let's see the first slide about these topics as well. So at the beginning of this lecture, we have one example. We have a function sine x to the power of cosine x, and we want to calculate the derivative of this function. This is a general rule that we will apply it in all part of the calculus, that if you have an exponent, we should use the exponential and logarithmic function. Why we should use the logarithmic function? Because we know that if we have the ln of, for example, ux to the power of vx, if we have an exponent like this, ux to the power of vx, then simply by taking the logarithm from both sides of the equation, this vx can comes out from the logarithm, and we can rewrite that one as a vx times ln of ux. So this is a property of a logarithm that help us to calculate the exponent by using the logarithmic function. So means that over here we have this property which is useful. The another property which is useful over here is about the e to the power of ln of u. We know that the e to the power of ln of u, since the logarithmic function, the natural logarithm and the exponential are inverse of each other, will be equal to u of x. Means that instead of ux, we can take exponential function then logarithm. Also, we can rewrite this expression like this. I mean, instead of writing e to the power of something, we can write it as an exponential of ln of ux. So again, with this notation, we can see that the exponential of logarithm of u of x is as the same as u of x. There is two notation for this situation that we just write both of them over here. So let us take a look at this example and see that how can we calculate the derivative of a given function. So let me name this f of x as y to avoid any problem about the complicated cases. So if I just do the same thing, means that write the left side and right side the same thing, means that I can rewrite that one as an exponential of ln of y. So I can do this one at the left side, and I can do the same thing at the right side of this expression as well. Means that we can rewrite it as an exponential of ln of that expression. Even you can leave it by take a logarithm from both sides, since the logarithm function is a one-to-one function. We can take a logarithm from both sides of that expression. Means that ln of y at the left is as the same as ln of sine of x to the power of cosine x. Right now, the exponent of this expression, which is the cosine of x, can comes out, or we can write it as a coefficient in the right side of this expression. Means that we can rewrite that expression as ln of y equal to cosine of x. It becomes the coefficient. I can write it like cosine of x as a coefficient times actually ln of sine of x. Right now I can apply the derivative for both sides of this expression, means that we can take a derivative from both sides of this expression, and if I take a derivative, the derivative of ln of y will be y prime over y, because this is the rule, chain rule for the logarithmic function. If you remember that ln of u was u prime over u. So at the right side I have a multiplication of two functions. So when we have a multiplication of two functions, we should apply the product rule. The derivative of the first one is minus sine x, the derivative of cosine is minus sine x, so it will be minus sine x as a derivative of the first one times the second one. The second one is ln of sine x, so I will write it over here, ln of sine x, and for the second part I should multiply the derivative of the second one by the first one. So let me just write the first one. The first one was cosine of x, so I will write it over here. Right now I should calculate the derivative of ln, and for writing the derivative of ln I said it before to sketch one straight line and write the same function at the denominator, which is sine x, and also write the derivative of sine, which is cosine, at the numerator. So it will be the derivative of right side of this expression. Right now we found y prime, so y prime over here will be equal to the multiplication of y by this expression, means that it will be y times this multiplication, this expression at the right side of the equation. So if I just grab it over here and put it over there, then we have this actually calculation. So at the end of the day we can find the y prime, and then y prime will be equal to the value of y, and the y is given by sine x to the power of cosine x at the beginning. So I can rewrite it as sine x to the power of cosine x, and that expression multiplied by this part of the equation, means that we will rewrite this part as well as a part that we have it here. So we can also have more exponent as well, means that x to the power of x or something like that, or even x to the power of x to the power of x as well. So let me just solve the derivative of that expression as well. So if we have x to the power of x to the power of x and we want to calculate the derivative of this expression, before that we continue to solve that one, we need to calculate the derivative of x to the power of x as well. Means that let us name g of x as a function that we have it over here, g of x equal to x to the power of x. Then let us calculate the derivative of this one first, means that let us calculate what is g prime of x, then we can evaluate x to the power of x to the power of x as well. So to calculate the derivative of x to the power of x, we use the same techniques. So means that we should take a ln from both sides. So I have ln of gx at the left side, and at the right side if I just take a logarithm from that one, then x will come out as a coefficient, so it will be x times ln of x. Right now take a derivative from both sides of this expression to calculate g prime. So if I do that one, at the left side I have g prime of x over g of x. This is the derivative of ln of g of x at the left side of this expression, and at the right side of that one again we have a product rule, so it will be the derivative of the first one, which is 1, times the second one, which is ln x, and we should add it by the derivative of a second one, which is 1 over x multiplied by the first one, which is x, and that x also can be cancelled from this expression. So at the end of the day we have ln x plus 1 at the right side. So by that discussion we found the g prime of x, or the derivative that we have it as a gx multiplied by that expression, and g of x is given by x to the power of x. So I replace g of x as a x to the power of x, and at the right side, as you can see, we have ln x plus 1 at the other side of that expression. So right now let us take a look at the derivative of x to the power of x to the power of x. If I take a logarithm from this one, again I have ln of y at the left side, and at the right side I have x to the power of x as a coefficient, and ln x as a value that we have it over there. As I said, it x to the power of x as a power of x is coming out from that expression. So this is the case that we take a derivative from both sides. Right now we have y prime over y at the left side of this expression, and at the right side we have the multiplication of two expressions. The derivative of x to the power of x is needed over here, so we have the derivative, we calculate the derivative over here, so we just substitute the derivative. The derivative of the first one, which is x to the power of x multiplied by 1 plus ln x, and the derivative of the first one should multiply it by the second one, so I multiply it by the second one, which is ln x, and the derivative of the second one, which is 1 over x multiplied by that one as well, so means that x to the power of x multiplied by 1 over x, or I can divide it by x. So at the left side then we have y prime equal to we should multiply both sides by y, which is x to the power of x to the power of x. This is y indeed, and I multiply the y by the given expression, means that by this actually expression that I have it at the right side. So we found this derivative. However, you can simplify it. For instance, over here x to the power of x over x can be written as x to the power of x minus 1, and we can simplify that expression as well by using that method. So at the next step we want to calculate the derivative of inverse trigonometric functions, but before that we reach to this actually concept and these topics, it's better to have a general review about the inverse of a given function. So previously we talked about the function. We said that when we have a function, means that there is one input and there is one output as well. So means that if we put x inside of this actually function, and f as a procedure or as a rule or as a function or mapping or transformation is working on x, then the output will be y, which is equal to f of x. And this is how can we schematically describe a type of the function. When we have a function, then also we can sketch the graph of a function by putting the value of x and y in a lines over there. Means that one horizontal line determine the value of x, and the vertical line determine the value of y. For example, over here, if the x and y is given here, so this is the value of x and this is the value of y, and for this x and y over there we have a point, so we can assign a point with the component of x and y. This is the meaning of the function. But what is the inverse of a function? The inverse of a function is determined by f inverse, and we put -1 at the top of f to determine f inverse of function. So f inverse is a function that we change the input and output of that expression. Means that inside of this inverse function, if I put the value of y or f of x, then the output of that one will be x. Means that its action totally inversely than the function f of x. Means that if I put that actually y inside of the function f inverse, then the output x is determined by f inverse of y indeed. So this is the meaning of the inverse of a function, and if we combine these two functions, the result will be identity function. So the another thing is about that right now, if I want to find the graph or the location of that point, then I should choose y in a x line and then choose x in a y line. I mean, I inversely should sketch that type of the graph right now. And if you just take a look on it, that y equal to x can be considered as one reflexing line over there. Means that if I assume y equal to x over here, y equal to x, then you can see that it's reflect the graph of these two functions. Means that the distance of the point from the y equal to x is as the same in both sides of this equation. So by this actually small the small discussion about these things, we can see that how we can calculate the inverse of a function. For example, if y is equal to x plus 1, and if I want to know what is the inverse of this function, so to find the inverse of this function, which is f of x equal to x plus 1, I should change the place of x and y. Means that instead of the x I will write y, and instead of y I will write x. So it will be x equal to y plus 1. And if I solve this equation respect to the y, then the result over there will be y equal to x minus 1. So means that if I have x plus 1 as a function, then the inverse will be x minus 1. So it's obviously correct, because when I put the input inside of this function, then I add it by 1, and the inverse function f inverse of x over here is given by x minus 1. I should subtract 1 from that expression. And if I just take a look at the graph of this function as well, you can see that the graph of a function satisfy this condition that I talk about. It means that if I just consider the graph of a function, the graph of y equal to f of x is y equal to x plus 1. So y equal to x plus 1 means that we have this graph indeed. So this is the graph of f of x, y equal to x plus 1, y equal to x plus 1. And you can see that this point, this intercept, the y-intercept is 1, and the x-intercept also is equal to minus 1. So, but if you just consider the y equal to x as well, so this is y equal to x. If I consider it here, so this is y equal to x, and right now the f inverse of x is on the other side of this equation. Means that that one was f of x, this y equal to f of x was given, and right now if you just sketch the x minus 1, the graph of x minus 1 will be on the other side of this case. So it should be exactly here. Okay, so we have the value of 1 over here right now, and minus 1, the another intercept, the y-intercept over here is minus 1. And as you can see, this is totally reflected by the y equal to x. So this is the inverse of that function. And how can we just calculate the inverse of a given function? So one of the most important cases that we can consider it over here is exponential function. So if you just take a look at the exponential function e to the power of x, then you can see the graph of this function as follow. Means that if this is the lines over there, the shape of that one, then the y equal to x is a function like this. I mean, it's increasing actually very quickly. So this is y equal to e to the power of x. And if I want to take a look at the inverse of this function, then I should change the place of y and x. Means that instead of y I will write x, and instead of x I should write y. Right now, if I just take a logarithm from both sides of this equation, then ln of x is equal to ln of e to the power of y, or y ln of e. And if you just take a look at the first lecture, we said that the ln of e is equal to 1. So by this words means that f inverse of x over here is determined by ln of x. So means that ln of x is an inverse function of exponential function as well. So means that ln of x is a inverse. So if I consider the y equal to x as well, this is y equal to x, then the inverse of that one will be the logarithmic function, and this logarithmic function also can be considered like this. I mean, if I can sketch it over here, it will be a function like this. So it's somehow functioning like this. So this is y equal to ln x as well. There is the another case that we have it. It's a case of trigonometric function. Each trigonometric function also has a inverse as well. So we can talk about the inverse of trigonometric function. One another thing we should consider about it is about the condition of having the inverse, that the function should have an inverse if it's a one-to-one function. Otherwise it cannot be inverse, because for one output input we should have one output as well. So let us take a look over here that what's happened. For example, if we consider y equal to sine of x, then sine of x is a function like this. I mean, it's like a mustache of a person like this. So it's continue up to the infinity. And also from this side as well, we have this actually shape of the oscillation. So over here this point is pi over 2, and the another one as well over here is minus pi over 2. At this point we have minus 1, the value of sine of x. So this is the y equal to sine x. If we want to have an inverse for this function, then we should change the place of y and x as well again. So if we do that one, means that x should be equal to sine of x should be equal to sine of y indeed. And we denote this function by sine inverse. Means that over here y is given by sine inverse of x, or arc sine of x, which determine the arc of the angle of sine as well, sine inverse of x. So this is not a power or exponent, it's only determine the sine inverse, and we can rewrite that one by the arc sine of x as well. So because the function should be one-to-one and this function is not, let me just mention that why it should be 1 to 1. So we said that we have a function if for one input we have one output as well. So look at it, for one x we cannot have 2y. So it's banned, it's forbidden to have this situation. And if the function f is given by not 1 to 1 function, then for 2x, for example, let me write it x1 and x2, we have one output, means that we have one output which is y. So when we inverse it, then for 1y we have two output which is not valid. So for this reason, for instance, for the case of arc sine, I just choose the interval between minus pi over 2 and pi over 2. And if I do that one, then by sketching the y equal to x over here, we can sketch the inverse of that function as well. So the inverse of that function is given over here by pi over 2, and this one is totally given like this. I mean, then we have 1 and minus 1 in this side. This will be the arc sine over there as well. So we can take a look at the decimals to have the better sketching there. As you can see over here, we have the graph of y equal to sine x, then y equal to x as a reflecting line over there, and this will be the arc of sine as well. So you can see the graph of this arc sine as well. So we can talk about the tangent as well. Let me just put the tangent of x, and then we can write the arc tangent as well. So this is the arc tangent, and as you can see, between pi over between pi over 2 and minus pi over 2, we should consider the inverse of that function, means that only one part should be restricted to sketch the graph of arc tangent. And we have the cotangent as well, and the arc cotangent over there as well. So as you can see, all of them are symmetric respect to the reflecting line y equal to x. So we can decide about their value as well, to see that what's happened over there when we have some value. For example, over here, if we assume a function like y, let us write it over here that the sine of, for example, pi over 2, we know that the sine of 90 degree or pi over 2 is equal to 1. So we have that value is equal to 1. Right now we can write it as a sine inverse as well. Right now the arc sine or sine inverse of 1 is equal to pi over 2. Arc sine of 1 is equal to pi over 2. So as you can see, the value of sine inverse, the value of the inverse trigonometric function determine the angle, not the actually value of that things. So because of that, it's determine the value of that, determine the angle or the arc of that corresponding value. So right now let us calculate the derivative of arc sine of x. The remains are the same, then I will list them over here to just keep it in our mind. So if I want to calculate the derivative of y equal to arc sine or sine inverse of x, then what shall we do? So this is the sine inverse of x, and if we want to calculate the derivative of this expression, first of all I try to inverse that expression, means that then sine of y, if I take a sine from both sides somehow, sine of y is equal to x. Right now I can take a derivative from both sides of this expression. Sine of u, I just emphasize about that the chain rule said that the sine of y, the derivative of sine of y will be y prime cosine of y. So it will be y prime cosine of y is equal to the derivative of the right side, which is 1. So we found out that the y prime over here is equal to 1 over cosine of y, but I should write everything in terms of x, not in terms of y. So for this reason I should change this expression somehow. We know that the sine of y is equal to x. It's given at the beginning that the sine of y equal to x. This is the relation between y and x. So I should change this cosine to that format. There is two forms of actually calculation right now. One form is using the trigonometric identity. We know that the cosine of y can be written as the roots of 1 minus sine square. So 1 minus sine square is equal to cosine square. 1 minus sine square of y is equal to cosine square, and then by taking the root you can find the cosine. So instead of the cosine of y I can put x, then I have 1 over roots of 1 minus x square. This is one method to reach to that formula. The another method is using the concept that we have it over here, this identity. So sine of y is equal to x. So to calculate the cosine of y I should sketch one right triangle, and in this right triangle let us name this angle as y. So the sine of y over here is equal to x, means that the opposite side should be x, and the hypotenuse of that right triangle also should be 1. Right now the sine of y is equal to 1. Let us calculate this side as well, the adjacent of y angle. So based on a Pythagorean rule, this one will be roots of 1 minus x square. It's very simple to just use the Pythagorean rule to calculate the adjacent, because the hypo square is equal to opposite square plus adjacent square, and the result determine the value of that one. Right now if I want to calculate the cosine of y, the cosine of this y will be adjacent over the hyper, which is roots of 1 minus x square, and you can simply substitute it over here. As I said it, we can use both of these cases as well. So for the other type of the trigonometric function also we have the same discussion. Let me just show one more example about that case. So for instance, if I want to calculate y equal to the derivative of y equal to tangent inverse of x as well. So to calculate that derivative, first of all I take a tangent from both sides, then it will be tangent of y is equal to x, and then I should take a derivative from both sides of this expression, and the derivative of tangent is equal to secant square of y. So it will be secant square of y times y prime. So let me put the y prime at the back. It's equal to the derivative of the right side, which is 1. So by that case y prime is equal to 1 over secant square of y, or cosine square of y, because it's gonna be the cosine square of y. Right now you can still use the identity to calculate that expression, or simply use the trigonometric relations over there. So again I just sketch one right triangle, and let us name this angle by y, and because the tangent of y is equal to x, so the opposite side should be x and adjacent should be 1. So by that discussion the hypo will be x square plus 1. So the first one is square plus second one is square will be the square of that one. So I need the roots as well. So roots of x square plus 1 will be the value. So right now if I want to calculate the cosine of y square, simply I can calculate the cosine. Cosine will be adjacent, which is 1 over the hypo of that right triangle, which is roots of x squared plus 1. This is gonna be the cosine, so it's cosine square, so I just square this expression, and the result will be 1 over x squared plus 1. This is too important in integration, so we will have this type of the expression in an integral too much, so it's better to keep it in your mind that what is the derivative of tangent inverse, which is 1 over x squared plus 1. So if I list all of them together, then I have the following table. So we can take a look at the list of this inverse trigonometric functions derivative, and as I said it before, the most important one is a tangent inverse, that I hope that you keep it in your mind, this type of the derivative. So the another type of the derivative that we should concern about it is the implicit derivative. Let us take a look at the implicit derivative now. So as you can see over here, the implicit derivative is our discussion right now, and the name declare about the concept. Indeed, sometimes x and y are twisted to each other, they mix with each other such that you cannot split them. For instance, if we have y squared x cubed minus for example plus sine of x squared plus y squared, let me just put some more complicated function to show that in this case you cannot always split them, and so we have x squared plus y squared inside of the sine, and let us put some ln as well, minus ln of x times y equal to x. For instance, if I have this type of the function, you can see that they are totally twisted to each other and you cannot split them somehow. Therefore, you can see that we cannot split y and x and write everything in terms of x or y. So in this case, we should take a derivative from all terms that we have it over here from left to right. So one more thing that we should consider it over here is about dy dx. When we use the chain rule, we just, for example, sine of y, if you have sine of y and we want to take a derivative of sine y, then the derivative will be y prime cosine y. But when we have sine x and we want to write the derivative of sine x, simply we will write it as a cosine of x. Indeed, over here dx over dx or x prime is 1, and it's no need to write it. So let us take a look on the expression. The first expression that we have it is y squared times x cubed, and when we want to solve this derivative or calculate the derivative, we should use the product rule. The derivative of the first one is 2y y prime. This is the case that I talk about it, so means that we should not forget the y prime. So this is the derivative of the first one times the second one, which is x cubed, plus the derivative of the second one times first one, and the derivative of the second one is 3x squared. So the x prime over here is 1, no need to write x prime over here. So 3x squared multiplied by the first one, which is y squared. Then we should calculate the sine of u. The derivative of sine of u is u prime cosine u. So let me just write the cosine u first, or cosine of x squared plus y squared. Then I should multiply this cosine of x squared plus y squared by the derivative of a terms inside of cosine. So the derivative of x squared is 2x, the derivative of y squared will be 2y y prime, so plus 2y y prime. And right now I reach to the ln, and as I said it before, when we have the ln, we should sketch one straight line and write the terms at the denominator, which is x times y, and then I should write the derivative of xy at the numerator. The derivative will be a product rule. The derivative of the first one is 1 times the second one y, plus the derivative of the second one, which is y prime, multiplied by the first one, which is x. and at the right side at the end the derivative of x is equal to 1. So we take a derivative from all terms that we had it right now. In this stage we should factorize y prime from the terms that they had y prime. So if I factorize y prime over here, then I have the following things. We have 2y x cubed for the first terms of the expression at the left side. The second one has no y prime, so I skip from that one. Then the first terms over here as well, we will take a look over here. So we take a y prime from the first one, the second one has no y prime, so I just keep it like this. And right now I multiply these terms by the bracket over here. The first one has no y prime again, but the second one has y prime, so I should consider this one as well. And if I just factorize y prime from that expression, then I have plus 2y multiplied by cosine of u over there, or cosine of x squared plus y squared. So let me just write cosine of x squared plus y squared. And for the last one as well, if I just take a look on the expression, the first term has no y, means that this term has no y prime, but the second one has the y prime, means that this one has a y prime, so I should consider this. And I have a negative sign at the back as well, so if I just factorize the y prime, the remaining part will be minus x over xy, that the x also can be cancelled. So this is the terms that has a y prime. Right now I shift the remaining terms to the right side. So to the right side I have 1, then I should shift that pinky part to the right side, and of course the sign will be changed. So we have minus 3x squared y squared, and moreover we have minus 2x cosine of u as well. So the cosine of x squared plus y squared should be written here. And also I have minus some terms over there that I should shift it to the right side, and if I shift it to the right it will be plus y over xy, that the y also can be cancelled with the y at the denominator. Right now I can calculate the y prime by dividing these two terms, means that at the end of the day y prime is equal to one fraction, that the right side should be written at the top of this fraction at the numerator, means that this part should be written here at the numerator of this fraction. So let me just sketch the fraction again. So, and the coefficient of y prime should be written at the denominator of that fraction as well. So I just keep that one at the denominator. So we can also solve one more example about that implicit derivative as well, but as much as you solve more example about this issue, you may get expert in that type of the topic. So I finish our lecture in this point, and in the next lecture we will discuss about the application of a derivative. So thank you for your attending.